This problem is the problem itself is just plug and chug, but it has an important practical application. All right, so what's going on here is that we have this closed cylinder um, uh, with a piston on one end. So you can just think of this as a syringe, right? So in fact, I looked up the diameter of a syringe. It's about 1 centimeter square, and that's where I got that number. So suppose I have this syringe, yeah, so you can just think of this as a closed, as a cylinder with a piston, and I can push this piston in and squeeze whatever is inside if I want. So this area is A. Okay. Now I have some water inside here. So I've got water here. And what I want to do is I want to squeeze the water by 1%. How much force would I need to apply? So what force do I need to apply here to squeeze the water by 1%, which means I want to squeeze its volume by 1%. That makes sense? Now, do you think it's possible to do that? Like, suppose you bring your, you give this little syringe with a certain amount of water inside, and then you ask your friends to squeeze it as hard as they can. Do you think it's possible to squeeze it by 1%? 1% would be a tiny little change in the volume. Is that possible? The answer is absolutely not. No matter how strong your friend is, you can bring a whole football team of very strong strong folks and ask them all to squeeze together. They will not be able to squeeze it at all, and we'll see why in a second. So how would you do this problem? So this is an example of bulk stress. So we can do bulk modulus is equal to minus delta P divided by delta V over V, because we are squeezing the whole volume. So minus delta P divided by delta V over V. All right. Now, let's figure out the delta P. So before you started squeezing, the pressure over here would just be the atmospheric pressure. So P initial would just be the atmospheric pressure before you started squeezing, right? And then after you applied that force, the new pressure, P final, is going to be atmospheric pressure plus whatever you added. So P atmospheric, because the atmospheric pressure is just continues to exist. Plus, let's say P is the pressure that you applied. That makes sense? So what is the delta P, the change in pressure? The delta P is going to be P final minus P initial. And can somebody work that out for me? P final minus P initial, what does that come to? Just looking at P initial and P final.
You just get P.
Yes, you just get P. Very good. So delta P is just P applied. I'll just call this P applied. That's the force applied by you by pushing on the piston. So we figured out the delta P part. It's the change in pressure. So that's just the pressure applied by you. And delta V over V, it's already given. It's 1%, so 0.01. So this is 0.01. 1% is 0.01, right? And so that is equal to the bulk modulus. Now, let's say the bulk, if you look up the bulk modulus of water, it's in the table that I had a few slides ago. That would be quite a large quantity. 2 times 10 to the power of 9 is the bulk modulus of water. That makes sense? So let's calculate P applied, and then from there we'll get force divided by area. So force, I'll just write it here. Force divided by area, that's P applied, divided by 0.01 is equal to 2 times 10 to the power of 9. And I'm just ignoring the minus sign because we don't care about that. My goal is to solve for F. So from here I get F is equal to 2 times 10 to the power of 9 times the 0.01, which I'll just write as 10 to the power of minus 2. And the area is also 10 to the power of minus 2 because it's 0.01 meters square. So times another 10 to the power of minus 2. That makes sense? All right. And so what does that come to? That's 2 times 10 to the power of 5 newtons. All right. That's an enormous, enormous, enormous force. 2 times 10 to the power of 5 newtons. How do we figure out how enormous that is? Let's think about that for a second. But is everybody clear about the calculation here? Calculation completely clear to all of you? All right, so let's just try to make sense of this 2 times 10 to the power of 5 newtons. So to get an idea of how strong that is or how much force that is, you can always figure out a weight. What is that the weight of? 2 times 10 to the power of 5 newtons. If you set that equal to mg and solve for m, now g is approximately 10, right? 9.8, so that's approximately 10. So that would be the weight of a mass, which is about 2 times 10 to the power of 4 kilograms, right? So that's 2 followed by 4 zeros, kilograms, approximately double it, and you get the pounds. So that's about 40,000 pounds approximately. So the force that you need to apply to squeeze some water by 1% is the weight of 40,000 pounds. That completely clear to all of you? Actually, the bulk modulus of water is not 2, it's 2.9, I believe. Let me just look it up really quick. I mean, I just wrote the 2 times 10 to the power of 9 from memory. So bulk modulus.
On the chart, it says 2.2 times 10 to the 9.
Okay, so it's 2.2. Okay, all right. So that was approximately correct, yeah. Or anyway, so that's you get approximately 40,000 pounds, right? And if I remember correctly, a Mack truck, fully loaded Mack truck weighs like 20,000 pounds or something like that, if I remember correctly. So you can see that this is an enormous, enormous amount of force that you'll have to apply to squeeze water even by 1%, right? And so there is, that's why we say, and the reason that this is happening is because of this enormous number for the bulk modulus of water. And it's not, water is not the only thing that has such a high bulk modulus. Most liquids have extremely high bulk moduluses. And that is why we say that liquids are incompressible. This is not a absolutely true statement. I mean, it's practical. It's a practical statement. I mean, you can compress the liquid if you can somehow muster up this much force, then you can compress it, but it's not practically possible. So for all practical purposes, liquids can be considered to be incompressible.